Okay, we have about 25 slides left, so we are done with MLR. Back to OpenML. So how can we now take some algorithm, some machine learning algorithm from MLR, run in OpenML, and then upload the results? Well, the answer is that's super easy. You just create the learning algorithm from MLR, so in this case maybe a random forest, maybe with a different hyperparameter setting. You get a task, yeah? So get OML task, task ID 37, would then download the task and download it to memory, to that task object here. It also always downloads it to disk. So after you have executed this statement here, also have a little, have a look at the console, yeah, that will tell you either downloading it to a cache directory or looking into the cache directory and then finding it there, which makes it, of course, a lot faster because you are then you can then work on the object without any further internet access, server access. And now the final command to tie this together is just run task MLR. So you run this learning algorithm on this task, and this gives you, again, a container object that contains this benchmark result, yeah, that benchmarks this algorithm on that task, yeah, and that BMR object contains already locally measured performance values, which OpenML will later recompute. And most importantly, it contains the predictions that will then be uploaded to the OpenML server and the information on the flow. So the BMR object is just that benchmark result. I already explained this to you, how this works in MLR. Then there's the flow. So the flow is all of the information we have extracted from the MLR learner object in a representation that's the same for algorithms in R and Python and in Java. Yeah? Or mtry is a parameter of, so I'm just showing how to also change, it's a hyperparameter. So the random forest does column sampling, yeah? So in the trees, yeah? So you randomly only pick a few features and not all of them, and the mtry is how many you take at each split point. Yeah? That's a very, like, the most common parameter of the random forest that you usually change besides the number of trees. No, I'm not training. I'm running the resampling procedure that OpenML tells me to run. So if you do this in your console, you will also see this in the logging output, where you can see, in this case, I'm pretty sure it will be a cross-validation, yeah, where you can see the 10 folds being computed. Yeah? That information is here in the task. Yeah? Yeah, that's what Joachim already showed you. Yeah, there are splits associated there. A splitting procedure, I would call this a resampling instance associated with the task. Yeah, all of that is downloaded. Yeah, so the task contains the data, the meta information, yeah, the target, maybe a performance measure that you are supposed to optimize, and also the splits. Yeah, and you can convert these objects also back and forth between MLR and OpenML. Yeah, and the yeah, yeah. Okay, so the question is, how often do I call the random forest? How often is this being applied and trained, right? Okay, first of all, mtry is not the number of trees. Mtry is another so that the number of trees would be n tree. That's the parameter. Mtry is, so, it's the column subsampling rate, the feature sampling rate, or the number of randomly chosen candidate features. Doesn't matter. You can just forget about this. I just put this into the example here to show that you can also change the settings. Yeah. Just to make it a little bit more interesting. And the answer, I mean, the more relevant answer to your question, how often is the tree being trained? The forest, my God. It's trained as often as there are training sets in the splitting procedure associated with the task.
Oh, okay. It is written inside.
Yeah.
So somehow it's quite similar
we are calling lapply inside of this. Yeah? Well, through many, many, many layers. Yeah? At the bottom, there will be an lapply. Yeah? No. Sorry. The question is, if I want to change the estimation procedure, do I have to create a new task? So if with estimation procedure you refer to, do I want to do 10-fold or 5-fold cross-validation, then the answer is yes. Then you have to create a new task. We have also auto-generated quite a few for many of the data sets on OpenML. But yes, if you just want to optimize or if you just want to measure different performance measures, then the answer is no, you don't have to do that because OpenML evaluates everything it can evaluate, every measure. Yeah? But for different splits, you have to create a different task. Okay, so flow is basically the general algorithm and the information about it, and the run describes the instantiation of that algorithm. Yeah? So the flow would mean, yeah, it's a random forest from MLR with a certain version number, and the run then says, yeah, I'm using the instantiation with mtry equals 2. Yeah? And that's, and the predictions. Yeah? So it's the instantiation of the flow plus the resulting predictions. Yeah? It's basically the experiment that you're running. Yeah? And here you can see this. We're just peeking into that object that is produced here by this run task MLR function. So here you have a short print out of the run itself. I mean, technically on the inside there's a more complex structure in there. You can see the task ID and a flow ID. Yeah? So the flow also gets registered on the OpenML server. And when this is uploaded, this will be registered at the server and filled in automatically. At the moment, we have only created this locally. And here you can see this benchmark result that I've shown you before. And here you can see the flow. So that contains lots of technical stuff that we are auto-generating. So which R version have you used? Which OpenML package version have you used? Which MLR version have you used? Which random forest package version? How many potential parameters are in there? So there are 20 parameters of the random forest that MLR knows about, and so on. And all of that information is then uploaded for reproducibility. And this uploading then is super simple. So you just take this run object and call upload OML run on it. And then you get also this run ID here, which allows you to identify the thing later on. So that's like a unique identifier in the database on the server to be able to refer to that thing later on. Of course, you can also search for this, because I know I uploaded this on a certain day, and maybe I tagged this. But if I want to really store away a precise pointer to that object, I can always use that ID, which is just the return value of the uploading call. Not sure whether I should click on this now. Should I give it a try? No? Shaking your head? I'm not even, I'm an idiot when it comes to Macs. We have it, okay. Clicking works the same on a Mac, I'm surprised. So here you can see the run, that's the ID. You can see it was run on task 37. We could also peek into that. Which does not work. You can see it was run on the diabetes data set. How do I now go back? Here? Like this? Okay. Sorry. Yeah, and we can see we used random forest, which was created from MLR. We can see the mtry settings here. We can see a seed and information about the RNG that was used, the result files, and I could now download the predictions in an R file. Yeah, I could just click on them and download them. If it's even possible. So Giuseppe, who was the maintainer of the package and is now doing most of the work, invested many, many days in making sure that you could basically take this algorithm, download it, on your system, and if you at least have all of the dependencies satisfied, you could recreate the same run. Yeah? You can rerun it in the same fashion. How do we go back to the slides? Here, like this? Tabs? I'm too stupid to do this, sorry. Ah, here, okay. It's in the browser. Okay, yeah, I'm really... But it's the... I have to go... Oh, yeah, my God. No. It's a bit late. Yeah, and when you upload the prediction, the server will auto-compute, I think, about 30 different performance measures on the predictions, like everything that it knows about it, that it can compute. So you don't have to select this specifically. So if this would be binary classification, it would, of course, calculate stuff like accuracy or error, but it will also compute all of these different ROC measures, true positive rate, F1, about 30. Yeah. Also, there are also timing informations uploaded to the server. That's a bit more difficult because if you run this on different systems, you have different hardware. We try to upload something that kind of measures how fast your hardware is that you have, that we can potentially later on normalize these timing settings. Yeah. If
you open it, you can see it.
Click on it again, you mean?
Yeah.
Here you can see this, yeah, so area under ROC curve, F measure, yeah. You can also see the stability of the measures across the different cross-validation iterations, and you even get performance measured per class. The kappa value, even some stuff that that I've never heard about, so KB relative information score, I don't even know what that is, and other stuff. That's just so I will go over this pretty briefly. So there are a bunch of converter functions because OpenML has kind of a hierarchy of objects, and a class structure, and MLR has that, and there are different converters. So you can convert an OpenML dataset to an MLR task. You can convert MLR tasks to OpenML datasets and tasks and flows and blah, blah, blah. So that helps you to either work in world A or world B with the different objects. That's, I think, most useful for programmers and not so useful maybe for normal users. And here we had another little practical where we told you to run your favorite algorithm from MLR on a task here specified with an ID, but you could also kind of pick yourself by searching for certain data sets or tasks. Maybe let's directly go to the solution. So that's super simple, right? So in order to select have a look at what's available in MLR, you can either go to the package tutorial and have a look at the appendix, what's available, or you can just say list learners, and list learners will list, well, a couple of hundred lines of different algorithms. You can also tell MLR not to worry about missing package installations. And then you can have a look at the class or the name and select something that you like there or the different properties and run this. Yeah? In this case, of course, my favorite algorithm, because it doesn't have too many dependencies, is rpart again. I'm just running this, uploading it. This is copy-paste basically from the slides, and you don't have to do much more. The one thing that I did here in the solution is to make sure that this is tagged with a useR 2017, so you can wipe this from the server later on. Yeah? And find these kind of spammy uploads next week and maybe remove them. We can then check if the upload worked by going to that website, checking out the predictive performance and scrolling down to evaluation measures, but I just did that for another run, so that really looks the same. Not.
Visualization, some way to see how simple and how elegant is this algorithm, because I think I would prefer an algorithm that's twice as simple,
yes,
but gives me 95% of the predictions of
yes,
the other algorithms. Is that contained in either MLR or OpenML?
Okay, let me repeat the question for everybody. So the question was, do we also have some measures of simplicity for certain algorithms, because the usual motivation is, so if I can take a very simple algorithm and that works nearly as well as the really complicated deep neural network, I rather take the linear model because I can analyze that much more easily and it's much faster. And the answer is currently no, we don't have that. So no. We store runtime. I mean, of course you can do stuff like, I mean, runtime tells you something else. Yeah, that's also often important for such an analysis, but
So for example,
yeah.
the measure I might want is, on average, how many features does it require to make this prediction?
No, we don't have that at the moment, but we are really interested in stuff like that. But it's not really technical supported in any way at the moment. You would need to make that judgment yourself at the moment.
You will be able to download lots of data, but it probably not much data.
Yeah, I mean, so I'm thinking in terms of that graphical display you had of like the history of analysis on this data set. You see the points that all people are, coming up with algorithms that are, increasing the prediction. This looks like they're just getting better and better, but I would also want to know, okay, but how complex are these algorithms? And as a user, I would find
No, I think that's a really relevant and good point. Yeah? You would only go to the really complicated stuff if you are kind of forced to, by the quality of the predictions. But at the moment, you would need to make that judgment yourself as a data scientist. Yeah? Okay, I think that's nearly that's the end of the practical. We can also now list the evaluation that we just uploaded. So if we would run this little command here, upload the run, we have to wait for a few seconds for the server to calculate the results, and then we can list them again. Here I'm using specifically the run ID, so that's just one object. Of course, I'm listing that, peeking into that, and I can see here, that was run really on task 37, and I can see the different different fields in there that tell me that was run with a decision tree. It was run on the diabetes data set, and I have then cut short the different evaluation measures there. Yeah, you see the area under the curve, F measure, and so on. So you can get back these results, and if I wouldn't restrict this so aggressively just to this specific run ID, if I would just request to list the results on the same task, I could compare now my result with, I don't know, what you guys maybe did yesterday. Yeah? So that's it from my side. Now Heidi would take over and walk you through tagging studies and cool stuff other people already did with OpenML. Can I use that? No. So let me try to repeat the question. I hope I got this completely. So you're asking whether we're using variable importance. Let me think about this. So first of all, variable importance is not supported by all models, right, in R, but by quite a few nowadays. So the random forest supports this, XGBoost supports this, various trees support this. If you can switch this on in the model, of course, and you upload the model, then this is also on the server. Maybe we could support this in OpenML a bit better. I think that's OpenML really doesn't know too much about it being there, but you could upload this. And MLR also now has generic variable importance, I think, through permutation tests, or at least we know that variable importance is computed in the model. We are not exploiting this, I think, at the moment as much as we could.
There's an issue that we end up higher on our list to compute this for all data sets.
Yeah.
Tell you which are more important than others.
I mean, the thing, even if we wouldn't support this for models in a generic fashion, we could just compute a random forest on each data set, and that would give you a lot of, insight already in what happens in the data set, yeah? Yeah.
We do have a meta feature that's called equivalent number of features. So it's a statistical measure that computes how many features are actually very useful. And that's a feature we compute for, that's a proxy we compute for every data set in OpenML. If you can zoom in into which one, that would be a
Okay, any more questions to the stuff so far? Okay, so tags. We already talked a little bit about tags. You've seen it before. Basically, you want to use tags to collect stuff. So for example, what if I want to collect a couple of data sets that I think are very interesting for me? Then I can use tags to say, okay, this is interesting, and this is interesting, and this is interesting, and then later I can find it again. And also, when I upload stuff, then I can add tags to it, as we saw earlier with the user17 tag, so that we can later find it again. So for example, if I upload a run, then I want to add tags usually to make sure I know why I uploaded this. So you can add tags to datasets, but also to tasks, to flows, and to runs. And the problem is then, of course, if I uploaded a tag that says Heidi's favorite datasets, then nobody else knows what that means, right? So you have no clue. So what we introduced to get a little bit more insight on the tags were studies. Studies are basically an extension of the tags, and they get their own website. And on this website, we explain what the task tag means. So if you go to the website, then you can click on this little plus button, and then you can create a new study. And there you can basically enter a title and a description. What does my tag actually mean? And then when I upload it, upload my runs or my data sets, then I can add the tag, study underscore, and then the number of the study. So your study, when you created this, so you click on this create button, then you get a study ID, and then you automatically have to use the study underscore 30 ID to add your runs or your data sets to this particular study, and then people will know what this tag means. This is very useful if you, for example, do a little benchmark study where you study algorithms and you want to compare them later on how well they did on different data sets. Then you can tag the data sets, you can tag the runs, and then in the end, you can just say, list all the run evaluations that are attached with the study 30, where I checked out how these algorithms here compare. So this object just includes some information on the data set, on the learner that was used, and also the predictive accuracy, and then I can create a nice plot where I plot the predictive accuracy on the y-axis and the different data sets on the x-axis and see which of my learners perform best over all these data sets. I can also use studies to, for example, check a new algorithm that you developed. You can just make sure that it's all collected in one study. Anything really where you want to add a description to a tag could be a study. Yeah, so in this little practical, we wanted to show a little bit how one can use a study, and so we selected this study 27 and wanted to ask you to summarize the performance results in this study 27 and look at the predictive accuracy. Maybe one thing that I wanted to mention here is if you don't know, for example, what predictive accuracy means, then we have a website that explains all of these performance measures, which has this very simple URL. And if you go there, then you get a description to all the performance measures that we have in OpenML. So if you want to do this, then we can just list the run evaluations and add the tag study 27. We get all the run evaluations and can plot this, for example, like this. Here I'm using a ggplot. I'm having at the x-axis, I'm using the setup ID. I'm going to explain in a little while what that means. And then the predictive accuracy on the y-axis. And then we have these three data sets that are called Haberman, LIMF, and SONAR. And I obviously seem to have different version of the SVM here. And I thought it might be interesting for you to go a little bit into the details of what information do I actually get back from OpenML about this, the runs that were run here. Because here I see that I have the setup ID, but I don't actually know what setup ID means, and I also get this information that I have two different versions of the run, but I don't actually know what that means either. So you might be interested in finding out more about the runs that were used here. So why are there two different versions of the flow is the first one. You can actually download the flows. So if you say, just give me the flow IDs, and I just need every flow ID once, then I can, then I get the flow back, and then I get all this information about the flows. And here you can see that the difference between the two versions is actually that there's a different R version, but there is also a different MLR version. And that's why there are two different versions of the flow. So for every change in package or in our version, you get a new version of the flow. But it always knows that it's somehow similar, just a different version. And then what do these different types of setup IDs mean? This is very algorithm specific here. We can get the information on the runs by, well, actually downloading the runs. So here with the get-OML run, I can download all the runs that where I have the evaluations for. And then I can use this command that's called get-OML run par list. It's a very long command, but it gives me back all the settings of the algorithms, or the parameters of the algorithms that were set. So I get here, for the first one, I get that fit is equal to false. Here the second is type equals to KBB SVC, and fit equals to false, and then another one has a different type. So the difference in the setup ID seems to be the type, actually. And the thing is that I only get back the information on what non-default values were set. So I actually have to figure out why what the default value of type is, because it's not included in this one, but it's included in the other two because they're not the default values. So to get that, I can first take these parameters and go into the parameter object and take out the type value. And so I get this, and I get NAs for wherever it's the default value. But MLR also knows what the default values are. So I have to first convert my flow to MLR, get the parameter set, and then get the default values. And then I get all the information on what the actual parameters are, and I can add this to my evals data frame, and then can actually plot this more sensibly here with the information on the parameter setting on the x-axis instead of something that I don't understand. So this is a little bit more tedious, but you can get all the information that you need, and this will also surely be easier in the future. So this is basically all about what you can do with OpenML, but And yeah, maybe, are there any questions so far? Okay, so yeah. Maybe you can answer. So the question was, how big is the user base?
You check it out for yourself. It's about.
Can you use this?
So if you go to OpenML,
It's muted.
But just turning it.
it's okay. Thank you. If you go to OpenML, here you see people. I think right now we have about we have about 3,000 people, I think. And if you look at statistics, at least I think 2,500 come back every month. So they're active users. And if you want to break down, I think it's about 1/3 academia, 1/3 industry, 1/3 students. Yeah, if you try this at home, you will see a full list of all people that you can see whatever.
Okay, so then I'm going to tell you a little bit about what people have been doing so far with OpenML. So we already talked a little bit about the bots, right? So you can have bots running on OpenML because you can just access it and it's all machine readable. Then you can use it for meta learning. We've also talked about this a little bit already, but I'm going to show you a little bit more about this in a minute. Then there's a big drug discovery study that we're also going to go into detail a little bit. Obviously, benchmarking is something that people are constantly doing with OpenML because that's what OpenML is actually super, super good at. And then you can also use it for algorithm checking. So if you created a new algorithm, or for example, recently we updated the C-forest algorithm, and we wanted to check on many different data sets if it actually works the way we want it to work. Then we can just use all kinds of different tasks and just run the new C-forest algorithm on all these different tasks. And this is a super nice way to check if your algorithm works under very different conditions. So missing values, no missing values, a lot of features, big data sets. So it's just very nice for testing new algorithms. So to go a little bit more into the bot, we have already talked about this in the first part because there were questions about it. So there's this one bot which is called OpenML Bot R, and it looks like this. And it's running on Azure, and it's already doing many runs every day. And basically what it does, it tries on many different tasks. It's trying a couple of different algorithms with a lot of different parameter settings. So for random forests, you need to set mtry, entry, and stuff. And it wants to fit. And the goal is to just try as many different things as possible. And the data sets that they're using are 75 data sets currently. More now? Okay, more now. And what they're doing with it is actually, so the goal of this bot is actually to do meta-learning. Meta-learning means you want to learn how to better set your default parameters of the algorithm. So here they're choosing, you can choose between different performance measures. And then, so maybe I should explain the graph first. So on the y-axis, you have the time, how long does the algorithm need to run. And on the x-axis, you have some kind of performance measure. Here, in this case, it's the AUC. And in this figure, so Bernd, you stop me if I'm saying wrong things. In this figure, every dot is actually, so one figure is for one data set. And here, the dots that you see are different parameter settings of XGBoost. So every dot is a run of XGBoost with a different parameter setting. And then the blue that you see here is actually the default setting for XGBoost. And with all these runs that they have already done, they can actually build a prediction model to predict which are possibly good parameter settings for XGBoost on this data set. Because it depends on the data set, obviously, right? So this is what they call a predicted Pareto front, which just says what are possibly good options in terms of AUC and time that I could use as settings for the XGBoost on this particular data set. And then the red dots are the actual best settings that you could have on this data sets, but obviously you know this only after you've run all the different settings here. Yeah.
Maybe a stupid question, but I don't understand why you have defaults for different data sets. Isn't the purpose of a default that it's data independent?
So the question was, why would you have defaults for different data sets? Isn't the default data independent, right? So in R, you have a general default that you always have, right? But maybe this is not the best way. Maybe for different data sets, you want to have different defaults, and you want to create your algorithm in the smartest possible way, right? But not run on a data set where other defaults would be way better with the same defaults every time.
Can I use that?
Yeah.
I can add a few comments.
Ah, he's turning it on. Thank you.
Maybe now? Yes. Okay. So, just think about for the random forest, right? What's the default for this mtry parameter? Do you know what this is in R? I mean, it's not 10. It's p, I think, divided by 3 for regression and square root of p. So p is the number of features, right? And I mean, I'm not sure whether it was Breiman or some of his later PhD students who came up with this formula, but how did they come up with that? I mean, they ran a larger benchmark. I mean, probably not on hundreds of data sets, but maybe on a dozen or whatever. And then they studied the performance and they looked at what works well, what works best, and it was not a constant value, but something that depended a little bit on data set characteristics, right? And the idea is just to take that principle now to the next level. So can we learn a function? And it doesn't necessarily need to be a completely trivial function, but something that depends on the data characteristics that then auto-sets these values. So whether you call this defaults or not, I don't care, but it's the point is sometimes you don't have enough time to do the tuning. No? I mean, of course, I'm really interested in creating powerful tuning algorithms, but some people don't have the time for that, to run that. And I mean, if we can create one configuration or a function that computes a configuration, just by looking briefly at the data set, then that must be worth something, right? And this is just trying out how far we can take that. And this tries also to take into account runtime, right? Because sometimes really the absolute best configuration that comes out of this function might be something that runs for 1,000,000 hours, but maybe you also want to have something that provides good results very quickly. So this is the idea where we are creating this Pareto frontier. So the idea would be you choose a certain algorithm, in this case maybe XGBoost, and you say, well, I want to optimize AUC. Now that's the measure that I'm interested in, and here's the data set. I want to work on that. Now how do I set the parameters? We call a little function and we show you this plot. And we basically show you, well, these blue points here, the estimated performances for all of the configurations that would be possible, and then you can select from this. And I mean, would you really go up to here, where it becomes super slow but not that much better? You're probably running this guy here, especially for first try. The thing is, it's not up to you. You can make that choice. We present this plot to you, and these blue points here, or the performances on them, are, well, this is what we call a surrogate model, right? It's basically, it's a not too trivial thing where we take dataset characteristics times hyperparameter configurations of algorithms and map them to each possible performance measure, and this we learn from these millions of results that the OpenML bot has already explored, And you can already, I mean, the thing is, R does a certain default parameter selection for you. So why not make this better if possible, right? Because very often these things have been set in a few seconds by package developers, because they didn't want to think about this, or in a careful manner by the authors of the random forest package, but they didn't do this completely data-driven. And we would just want to try to do this as well as we can learn from data. I mean, as machine learners, we're good at that. So let's just do that also for machine learning algorithms. Sorry, that was a long answer.
No, it's good. One more question, yeah? Yeah, so basically what you would usually get is only the violet dots, right? That's what you get, and then you can run it, and then you can see also the other dots, but that's your goal, that you want to be able to predict what the best parameter settings of your algorithms is for a new data set. The data set, the data set characteristics are the independent variables, yeah.
And the hyperparameters of the algorithm. So it's twofold. So the one thing you basically observe when you have the data set, you can observe the characteristics, and the other thing is what you control. So we have this larger regression model where you kind of fix a certain subspace and then optimize over the remaining space. And it doesn't give you the best configuration, it gives you a bunch of non-dominated configurations there where you can select. Do I more care about runtime, or do I care about really last epsilon predicted performance? And to get multiple, you get optional configuration, a spectrum of configurations. No, the characteristics of the data sets are the independent variables. So number of observations, number of features, number of missing values, number of classes, and OpenML actually computes, I think now, more than 100 meta-learning characteristics from this Fantail library.
That clarifies my question from before.
Yes, Aaron?
It's a joint model that we are learning. So we're learning a joint. So imagine, let's keep it simple. So you just have 5 dataset characteristics. NP, time, number of classes, number of missing values, or whatever. And then you have XGBoost, and that has maybe, I don't know, 10 hyperparameters. And then there's just one performance measure because you're always interested in AUC. We just do that for every measure. And you learn a model on the joint space of dataset characteristics times hyperparameters, mapped to AUC. And also mapped to runtime, and also mapped to classification, error, and so on. And for this specific project, we always look at the measure and the runtime. So there are always 2 models involved. And so these models are really learned jointly on all of the hyperparameters and even all of the dataset characteristics. Sometimes this is called an empirical hardness model. Or no, sorry. How does Frank call it usually? It's empirical hardness model, right? Yeah, I just call it dataset characteristics times hyperparameters model. And the thing is, it's interesting because like half of the space you can observe, you can control, and the other half you can then optimize over, right? And you can ask for, do I get good? Is that probably a good thing to set it like that? What would the estimated runtime be? What would the estimated quality be? This is an ongoing research project. This is what we currently have. We are not completely done yet. But the idea would be in R to kind of show you that plot when you have a new data set, and then you could try out a configuration from that. If you don't care about runtime, you just optimize then for performance. This you could even do. This you could do fully automatically. And if you care about runtime, you can say, well, I'm taking this guy here, which seems to be 10 times faster, but maybe just an epsilon worse in performance. And if you want to know more about that stuff, we can also discuss later during the reception.
And now Joaquin will tell you a little bit about the drug discovery study.
Cool. Thank you. So you can also use OpenML, of course, to do real science work. And one example of that is drug discovery. So you may know that there are a couple of, well, a large number actually of diseases which are called rare diseases, which are relatively rare. It means that less than 1 million people get them. But these diseases, they still kill a lot of people, a lot of children. But they are not attacked by the pharma industry because there's just not enough people having these diseases. And the reason is that the reason why it's so expensive to test, to develop new drugs, is that you have to test drugs on many different proteins. Right? The way drugs are developed is you have a molecule, it's a drug, or a compound, and you want to find a compound that inhibits a protein. And if you inhibit a protein, you can also kill the virus or the parasite that requires that protein. Right? So you have a protein, you want to know which molecule inhibits the growth of that protein. And that's very expensive work. That's wet lab work. You have to do have to hire a lot of people doing experiments and so on. So, can we use machine learning to make that better? It turns out there's a very nice database called the Campbell database, which has over 12.8 million of those experiments on 1.4 million drugs on 10,000 proteins. What we do here is we want to build an algorithm that tells you how to build a model that predicts which molecules are very likely to work well against this protein. So what we did, we took the Campbell database. This is worked together with, among others, Ross King in Manchester University. So what we do, we take those 12.8 million activities, and we create 16,000 what are called QSAR datasets, one dataset per protein. And then these datasets consist of all the molecules in the row, all the drugs, and in the columns, they're all the fingerprints. The fingerprints are properties of the molecules that are automatically extracted by other tools. And then we get over 2,700 of these datasets because some are just too small, so I have to remove them. And we tried 6 different feature representations. So the question here is, how do you represent the data? Then how do you model the data? And the current state of the art is basically to use random forest for this, which works reasonably well, but we can do much better if we use a meta-algorithm that looks at the QSAR dataset and then tells you, okay, for this data, you need to use these fingerprints and these machine learning models, and then it can give you a much better model to predict which drugs are active. So we tried that. That's going to appear in a machine learning journal soon. We got much better results. So now we can so now these 16,000 QSAR datasets are also available in OpenML. So if you are in this area, you can just download them and develop your own models to develop drugs faster. And this really allows small and big companies to develop new drugs faster. That's stage 1. And stage 2 is now because we have these features which are calculated by standard tools. Now we also want to use machine learning to actually calculate optimal features for this. And this is also turning out to be very promising. That's just one example. Thank you.
Okay, so now we've talked a lot about what OpenML is and what the features are and what you can do with it and what other people do with it. And of course, this is an open source project, and we're very welcoming and very nice. So, and we need a lot of help because this is completely, at the moment, volunteer-based. So if you think OpenML is great and if you have ideas for new things that one could possibly do with OpenML. We had a lot of questions of people, can you do this, can you do that? And sometimes we had to say no. But of course, it's up to you to implement it. So please come and help us. So we have twice a year, we have hackathons where we meet for a week and write code together, work on tutorials, work on making OpenML better, but also where people who want to use OpenML can come and join us. And the next hackathon is more user-focused hackathon, and it's in October. So if you're interested, just come to talk to us, and yeah, then you can probably come. So It's going to be in Leiden, in the Netherlands. So it's a very nice place, and we had a workshop there before, and it was really, really nice rooms, and it was really cool. So it's always very much fun, a lot of work, and pizza. And if you want to contribute remotely, we have a wiki page where you can check out how you can help or how you can get involved. But basically, I think anyone can really get involved. Even if your programming skills are not super high, then you might want to help with the documentation or creating tutorials like this, or helping reach out to people who might want to use it, or helping to network. We need help in many different ways, so don't be shy and just come and join. And then, yeah, this is the end. I want to thank all the people who are already involved, because it's a very cool group of people. And they're doing a lot of really hard, cool work, and most of it is basically in their free time. So thanks to them for that. And yeah, if you are interested in more or have questions or anything, we're around the whole week, so come and talk to us. That's it.